So we have this situation. The scenario is two carts with a spring we can see. It's compressed. So this is very much like the lab we did in class. But it looks like before there's an explosion, the thing has an initial velocity. So it looks like it's already moving in that direction, and then it's going to explode, is what it looks like. In which case, this one's velocity will increase, and this one's velocity will decrease. So that's what it looks like it's happening. Now we have a graph, so we'll do an Oizerga analysis on it. The origin's right there. Velocity in normal units, time in normal units. So velocity and time. So therefore, any question about velocity and time will simply be read off the graph. The gradient delta v over delta t is acceleration, and the area is v delta t, which is the displacement. So we see there's two cars. This one car is moving at a constant velocity of 2, and it goes faster. So that looks like it's the 2 kilogram car. Yes, that looks like that one's going to go faster. And then this one goes slower, like so. So now we read the question. We have two carts, mass and 1, travel together at time 2 seconds. At 2 seconds, the spring inside the two-car expands. And so it expands, and of course what we see occurring is the velocity changes. Notice that the delta t's are the same for both of them. And this one increases its speed, and that one decreases its speed like we predicted from the picture. It shows a graph of the velocity as a function of time. What is the magnitude of the change in linear momentum of the two-cart system between t0 and 4 seconds? So we have our initial momentum, which has a mass of 3 kilograms, and the velocity is 2, so we have a total momentum of 6 kilogram meters per second. And afterward, we have the momentum of the 2 kilogram cart, so that's 2. And that momentum we see now is 2.5. So that is 5 kilogram meters per second. And the momentum of the one car is its mass, which is 1, times its new velocity, which is 1. So it has 1. So we have 1 kilogram meters per second. So beforehand, we had the two cars together system, and that's the 2, and that's the 1. We can see 5 and 1 is 6, and the total before and after are 6. So the change is 0 kilogram meters per second. The momentum of the system remains constant. Now, another way to think about this system is that we can take the system and represent it by one dot. We reduce it to its center of mass where all the mass is. So now we have a 3 kilogram object that has this momentum of 6. With a 2 meters per second velocity. Now, if we forget that there are two carts, and we're looking at this object that has a center of mass located here, moving at 2 meters per second, did this two-cart system have an interaction with any other body? And the answer is no. This two-cart system is an entity by itself, and it didn't have an interaction with any other body, so its momentum should stay the same. So zooming out, we can go through the details and do the accounting to show that the momentum is the same. But we could approach this question from this perspective, looking at it as a one-body system. The system has momentum. The momentum of the system remains constant. So unless there is some other body that interacts with it, the momentum will remain constant and the change in momentum will be 0.